This video is about areas between curves and how we can use slicing to set up a definite integral for these areas. I recommend that you watch my other video first, which is available on YouTube using this link and QR code. Our goal is to use slicing to set up an integral for the area between two curves f and g that are continuous on an interval from a to b. Suppose f of x is greater than or equal to g of x for all x in the interval. We can create a slice at a representative x value x star. We can think of this point as having coordinates x star, comma, f of x star, and this point has coordinates x star, g of x star. So the height is f of x star minus g of x star, and the width is delta x. So the total area when we integrate over all the x values from a to b is the integral from a to b of f of x minus g of x dx. This formula works as long as f of x is greater than or equal to g of x for all x in the interval, even if one or both curves are below the x-axis, since f of x star minus g of x star will always be positive or zero. Let's do an example. Find the area between the curves f and g on the interval from 1 to 4, where f of x equals 1 over x and g of x equals the square root of x. Now we have to be careful because just because the first curve is called f and the second curve is called g doesn't mean that f is above g on the graph. We'll have to sketch the curves to see which graph has greater y values on the interval from 1 to 4. So sure enough, if we remember what these graphs look like, here is the curve square root of x, and here is 1 over x. They actually intersect at x equals 1. We'll have to talk about that in a later example. But between 1 and 4, we can see that g of x is actually above f of x. So the area of a representative slice is g of x star minus f of x star times delta x. In other words, the square root of x star minus 1 over x star, all times delta x. So the area of the region is the definite integral from 1 to 4 of the square root of x minus 1 over x dx. You're welcome to pause the video to look at details, but the answer you should get is 14/3 minus natural log of 4. That's the area of this region. For our next example, we're going to find the area enclosed by the curves f and g, where f of x equals negative 3x plus 1, and g of x equals x squared minus 3. Now, what do we mean by enclosed? If we draw a sketch to see the region, f of x is just a line with slope negative 3, y-intercept 0, 1, and g of x is a parabola that opens up with vertex 0, negative 3. And so when we draw this sketch, we can see that there is a region enclosed by these curves. And we can see that f has greater y values than g in this region. But where do the curves intersect? In order to figure out what the limits of integration are, we will need to know what the leftmost x value is and what the rightmost x value is for the region. Notice this point is on both curves, f and g. So whatever this x value is, we could plug this x value in to f to get the y value, but the same y value comes out when we plug it into g. And that gives us a clue as to how to find what question mark is. And it's the same over here. We can set the y values equal and solve for the equal x values. So when we set f of x equal to g of x, we get x equals -4 and x equals 1, which is plausible given our sketch. This is now x equals -4, and this is x equals 1. In fact, if we plug in -4 to either f of x or g of x, we will get 13 out. So this is the point -4, 13. And if we plug in 1 to either function, you can check that we get -2. So the points -4, 13 and 1, -2 are on both curves. So the region lies between x equals -4 and x equals 1. So the area of the region is the definite integral from -4 to 1 of f of x minus g of x dx. In other words, the integral from -4 to 1 of -3x plus 1 minus the quantity x squared minus 3 dx. Evaluate this definite integral, and you should get 125/6. Another example, find the area between the curves f and g on the interval from 0 to 3π/2, where f of x equals sine of x and g of x equals sine of 2x. Now, if we don't know exactly what the curves look like, we can find the essential information by working out where the intersection points are and then test in between for which curve has larger y values. So first, setting the curves equal to each other. This step requires a trig identity. One of the double angle identities is sine of 2x equals 2 sine of x cosine of x. So that's what I'm using here. We get down to sine of x must be equal to 0, or cosine of x must be equal to 1/2. Sine of x equals 0 at each multiple of pi. The cosine of x is equal to 1/2 when the reference angle for x is pi/3, and the angle is in quadrant 1 or quadrant 4, because it has to be positive. So we get these x values. Now we are only interested in the interval from 0 to 3π/2, so the x values at which the curves intersect on this interval are 0, pi/3, and pi. Now we can test values in between the intersection points to see which curve has larger y values. The intervals we need to test are from 0 to pi/3, from pi/3 to pi, and from pi to 3π/2. For example, between 0 and pi/3, we could use pi/4. The sine of pi/4 is root 2/2. The sine of 2π/4 is the sine of pi/2, which is 1, which is certainly greater than root 2/2. So g of x is greater than f of x on this interval. We can repeat this process for the other two intervals, and we get that g of x is larger from 0 to pi/3 and from pi to 3π/2, and f of x is larger between pi/3 and pi. So now we're ready to set up our integral. We will need 3 separate integrals corresponding to the 3 subintervals. The total area is the integral from 0 to pi over 3 of sine of 2x minus sine of x dx, plus the integral from pi over 3 to pi of sine of x minus sine of 2x dx. Notice that we put f of x first for this integral because sine of x is larger than sine of 2x on this interval, plus the integral from pi to 3 pi over 2 of sine of 2x minus sine of x dx. Now, of course, if you do know what the curves look like, that's good because we can do a reality check to make sure that the intersection points that we found are plausible. So here we are at 0, the curves intersect. They also intersect at pi over 3 and at pi. And here is 3 pi over 2. This is sine of 2x, which lies above sine of x, on this first interval. Then sine of x lies above sine of 2x between pi over 3 and pi. And finally, sine of 2x is above sine of x for the last interval. As far as evaluating these integrals, I encourage you to pause the video and try to compute them yourself before continuing. Here are some details if you want to check your work. You should get a final answer of 9/2. Here's our last example. Find the area between the curves f and g on the interval from 0 to 3 pi over 2, where f of y equals sine of y and g of y equals sine of 2y. Now you might notice that this looks very similar to example 3. The only difference is that y is the independent variable this time, and x is the dependent variable. So the interval from 0 to 3 pi over 2 represents y values. The problem is done the same way, except we now look for which function has larger x values on each interval. Graphically, this will be the function on the right rather than the function above. When we're looking for x values for which the y values are larger y values are ones that occur higher up on the graph. Whereas when we have x as a function of y, and we're looking for which values of y have greater x values occur further to the right on a graph. So this is x equals sine of y. This curve is x equals sine of 2y. So sure enough, from 0 to y equals pi over 3, we have that sine of 2y is larger than sine of y. So it has larger x values, meaning output values. Between y equals pi over 3 and y equals pi, sine of y is greater than sine of 2y. And finally, between y equals pi and y equals 3 pi over 2, sine of 2y has larger x values than sine of y again. So the total area is the same as what we had before because the integrals are identical, except that x has been replaced with y in all cases. In summary, if f and g are continuous functions on an interval from a to b, and f of x is greater than or equal to g of x for all x in that interval, then the area between the curves is the integral from a to b of f of x minus g of x dx. To determine where f and g intersect, set f of x equal to g of x and solve for x. I recommend that you sketch the curve and/or use test points to determine which curve has larger y values on each interval. If the curves cross at some value c between a and b, then set up separate integrals for the intervals from a to c and c to b, and repeat that process as many times as you need for all of the intersection points. And finally, the same steps apply if x and y are switched. If you have functions of y instead of functions of x, just switch x and y throughout. I hope you found this video helpful.